In this video, we're going to talk about electron transfer reactions, otherwise known as oxidation reduction reactions, otherwise known as redox reactions. Now, if you recall from our previous video, our oxidation numbers, oxidation reduction reactions can be tracked using oxidation numbers. And oxidation numbers can simply be found just by following a few simple rules. So I invite you to go back and look at my video on those rules using the link above. Now, what we can see though is if we do that, we can see that some atoms or species are going to lose electrons. So in this case, zinc is going from no charge to a positive charge. And so to go from no charge to a positive charge, you have to lose electrons along the way. And the copper here is going from a positive charge to no charge, so it had to have gained electrons along the way as well. The process of losing electrons, as we discussed in that previous video, is oxidation. And the process of gaining electrons, in the case of the copper here, is reduction. Now there's two other terms in here that we need to be aware of because they are different and new. And that is the idea of a reducing agent and an oxidizing agent. So what are those things and what do they have to do with oxidation and reduction? Because it seems kind of backwards, right? An oxidation is forced by a reducing agent. A reduction is forced by an oxidizing agent. That doesn't seem to make sense. Why is that the case? Well, if we look at it from the standpoint of our terminology, the term oxidizing agent means that the substance is forcing oxidation of another reactant. And if a substance is forcing something else to be oxidized, well, oxidation is the loss of electrons. That means that the oxidizing agent is forcing electrons to become free. Well, the oxidizing agent is going to grab those extra electrons, and having extra electrons, gaining electrons, that's reduction. So that's why the terminology seems to be backwards here. We get a reduction in a substance because it is forcing something else to lose electrons. And on the flip side, a reducing agent is forcing the reduction of something else. So a reducing agent is forcing something else to take electrons. Well, where do those electrons come from? Well, they come from the reducing agent itself. And so the reducing agent gets oxidized in the process. So it seems kind of backwards, but in reality, it's very sound. The idea that an oxidizing agent is going to gain electrons because it is forcing something else to lose them, and a reducing agent is going to get oxidized because it's forcing someone else to take their electrons, does make good sense if you think it all the way through. Now let's take a look at an example. Here we have a reaction between hydrazine and dinitrogen tetroxide, which creates nitrogen gas and water vapor. And this combination of gases through this reaction is what rockets actually use to create propulsion. The ignition, the reaction of these two species create far more gas than what was present before, and that gas outlet is what pushes the rocket to go from one place to another in outer space. Now the question here is simple. Identify what's oxidized and reduced. Identify the oxidizing agent and the reducing agent. Okay, so to do that, I need to identify oxidizing and reducing. I need to identify my oxidation numbers. And so if we follow our logic and our lead, we've got 2 nitrogens and 4 hydrogens equaling no charge. And if I follow this all the way through, 2 nitrogens plus 4 times positive 1 for the hydrogen because it is bonding with a nonmetal, so hydrogen's positive 1 in those cases. 2n plus 4 equals 0. 2n equals negative 4, and so n must be negative 2. So I've got a negative 2 on the nitrogen here. I've got a positive 1 on that hydrogen. I can follow similar lines of logic for the others. I would get a positive 4 for the nitrogen here and a negative 2 for the oxygen there. I would get a 0 for the nitrogen in the product, and I would get a positive 1 for the hydrogen and a negative 2 for the oxygen. And so if you're having trouble still with oxidation numbers, why don't you pause the video right now and just kind of work your way through the algebra like this and try to come up with the same answers that I did. And that should help a lot. But for the rest of us, let's go ahead and move on from here. And so what we can look at and see is that this nitrogen here in the hydrazine went from a negative 2 state to a 0 state. So we went from negative 2 to 0 in that one. That would be an oxidation. And the nitrogen in the dinitrogen tetroxide went from positive 4 to 0. That would be a reduction. So to answer the questions, what are oxidized and what are reduced, the nitrogen in hydrazine was oxidized. The nitrogen in the dinitrogen tetroxide was reduced. Now, what is the oxidizing agent and what is the reducing agent? Here's where we have to be careful. These terms, oxidizing agent, reducing agent, the term agent here really means one thing and one thing in particular. I need the full reactant that contains the element that was oxidized or reduced. So to that end, the nitrogen in hydrazine was oxidized. That means that the hydrazine itself is the reducing agent. And the nitrogen in the dinitrogen tetroxide was reduced. That means that the dinitrogen tetroxide is the oxidizing agent. So it's not just nitrogen that was the reducing agent and nitrogen being the oxidizing agent. That's actually fundamentally incorrect. It is the reactant that contains them that is the oxidizing agent or the reducing agent. So this is how we can begin to identify oxidizing and oxidation reduction reactions through the oxidation number method here to identify the movement of electrons that is taking place, as well as the reagents that are causing those movements to take place as well. The next step out of this is to start looking at balancing redox reactions. Now, balancing redox reactions are difficult tasks. This is probably going to be one of the hardest things I ask you to do in all of this course. Because not only do you have to account for elemental, atomic kinds of balancing, you also have to account for all of these electrons. And so there are two primary methods for doing the redox reaction balancing. I'm going to focus on something called the oxidation number method. The reason I focus on this one is if you can do oxidation numbers, it's really quick to solve these because it becomes a matter of a series of relatively small steps that you can use to balance. There is another method out there. The other method out there is called the half reaction method. And it is useful, especially if you aren't as good at doing oxidation numbers. The problem with it, it's more steps and it can take a lot longer to do. And so the purpose of the next video will be to feature the oxidation number method and do a couple of examples with it. Again, if you're interested in the half reaction method, I will put some links to the half reaction method in that video so that you have some other ways of going about doing it. But until then, have a good day.